So, we're on a new chapter. State space models. So we are done, but we're never really done, right? With linear graph models. Now we're going to do state space models. Turns out, we're going to construct state space models from our linear graph models. So we're in the same nightmare. Okay. So, I'm just kidding. I love it. So, I hope you guys will love it too. Okay. State variable system representation. State variables, typically denoted x sub I for the ith state variable of a system, are members of a minimal set of variables that completely express the state or status of a system. All variables in the system can be expressed algebraically in terms of state variables and input variables, typically denoted ui for the ith input. Okay? So we've talked about input variables before. State variables are sort of a new idea, right? But input variables and state variables together can describe any other variable in the system. Okay? A state-determined system model, which we've talked a little bit about before, we're going to be a little bit more explicit about it now. A state-determined system model is a system for which the following three conditions apply. So first, a mathematical description is given in terms of n state variables, xi. So maybe you have a system that can be described by three state variables. So n would be 3, and you would have x1, x2, and x3. Okay? The second condition is that there's an initial condition for each of these state variables. So maybe if we had three state variables, x1 at time equals 0, x2 at time equals 0, and x3 at time equals 0 are all given. Okay? And finally, the third is that we know the inputs, each input, u1, u2, u3, u4, however many inputs you have, for all of time greater than the initial condition, and for the initial condition, initial time. So these three together are sufficient conditions to determine xi for all of time greater than the initial time. So if you're given the states at the initial time, and you're given the inputs, and you have a mathematical description of the state-determined system model, then we can find what the states are going to be for the rest of time. Okay? We call n, which is the number of state variables required to describe the system, the number. We call n the system order. Okay? So that mathematical description from part 1, we're going to talk about in the next lecture in detail. But that mathematical description is essentially a set of differential equations. Okay? And this should look kind of familiar to you guys, right? Mathematical description. So, differential equations. Initial conditions, so initial conditions, and inputs for all of time, so our source variables given. If you have those, you can solve for state variables for all of time. And it's familiar because we've been doing it without all of this terminology around it already for circuits, right? So now we're just doing it more systematically, and we can apply it to more different types of systems, So these state, input, and output variables are all functions of time, right? So state variables, functions of time. Inputs, sources like the voltage source might be sinusoidal or something. Function of time. Output variable is also a function of time. Maybe we care about what the position of the mass is or something like that. That would be an output variable. So typically we construct vector-valued functions of time for each. Okay? So instead of saying we've got like x1, x2, x3, x4, x5, we're going to just say we have a state vector x, which this is bold, maybe hard to see on the screen, but it's bold, is actually, the state vector, so-called state vector x, it brings together all of the different state variables into one vector, okay? Which actually makes it a vector-valued function of time. Okay, so it maps a time to an n tuple. If it was a two-state variable system, it would be a double. If it was a three-state variable system, it would be a triple. If it was an n-state variable system, it would be an n tuple. This is literally what it's called. I know you guys don't believe me, but it's true. I'm not even bullshitting you guys. So, all right. So, for real, I would never do that. Okay, I would do that, but I would tell you if I was. Okay, so the ith value of the state vector is the state variable xi. Okay, so pretty much take all of the state variables and we just stick them in a vector. We typically use a column vector, although that's not fundamental. That's just conventional. Similarly, the so-called input vector u is actually a vector-valued function of time as well. And so we put it in an R vector, an R tuple with the R different inputs. So if there are inputs, you have to have a vector of them that's R in length, right? The ith value is denoted u sub I. Okay. So, not too surprising. And then finally, the last one is the output vector. So we take all of the outputs and we also stick them in a vector. Because why? We don't want to write them all the time. That is tedious. We don't like that. We are pretty lazy, it turns out. That's why we have computers and stuff. Okay. So we write it as a vector of outputs as well. Most systems encountered in engineering practice can be modeled as state determined. Okay, so this definition that we just described of a state determined system that can be solved for the states for a function of time as functions of time. Most of our engineering systems can be modeled this way. For these systems, the number of state variables n is equal to the number of independent energy storage elements. So we define n, the system order, to be the number of state variables, which is the minimum set of variables needed to describe the status of the system. But it turns out that it's also equal, so the order of the system is also equal to the number of independent energy storage elements. An example of energy storage elements that are not independent would be capacitors in parallel, for instance. They share the same voltage, therefore they cannot be independently varied, right? So that would be an example of one. We'll talk more about dependent energy storage elements later on down the road, but just to give you an idea, it's roughly the number of energy storage elements, but they have to be independent, which most of the time they're independent, but sometimes you'll run into one that's dependent. You gotta lump it in. So we'll talk about that later. All right, so let's fill in this block diagram. So we have our inputs, they go into the system, which is described by state variables, right? And then you have outputs that come out of the system. So let's write on here what our input vector would be. Remember, we call it an input, we call it a vector, but it's really a vector value function. Once again, another proof that we are lazy. Okay. We can't even finish the whole thing. We just say vector, and often we'll just say u, the input. We don't even say vector. Like we get that lazy. I'm surprised we don't just call it the I. That would be enough, probably. Okay, so the input is the vector that is each input variable has a function of time. So u1, u2, all the way down to u. And there we used the letter r to be the number of inputs, so there are r of them. So it's an r vector, you could say. So those go into the system. The system has inside of it these state variables, right? So we write the state vector as being x1, x2, down to x, and there are n state variables, so xn of t. So whatever happens in the system happens, and then, so inputs come in, states are affected, and then outputs come out, right? So our output vector is y1, y2, down to y, and we said that the letter we use to specify the number of outputs is m. So let's just like down here in the margin come up with a little like inline example. So we're familiar, yes, with mechanical and mechanical translational and rotational systems, but we're most familiar at this point in this class with electronic systems, right? We've been doing a lot of analysis of those. So let's do an example with an electronic system. And I'm not even going to draw a circuit, but let's just say you had a circuit with 3 sources in it, okay? It's a lot of sources for this class, but just to show that we could do 3, it's just 3 lines, so we can do that. That's no problem, right? So this is the nice abstraction we're using, right? So our input with the 3 sources, maybe we have 2 voltage sources and 1 current source, okay? So the input would be a 3 by 1 vector, and they can go in any order, so the order is not important. You just have to pick one and stick to it. So let's just say like voltage source 1 was the first one, voltage source 2 was the second one, and then current source, well, we don't even need to give it a 1 because there's only one of them. Those are our 3 input variables because those are our 3 sources. Okay? So 2 voltage sources and a current source, so there are 3 input variables, and our input vector is defined as this. Okay? So the system, whatever system you're given, is going to have sources, and those sources determine what the inputs are. Okay, now let's say that, so we don't know how to construct our state vector yet. We don't know how to choose our state variables yet. But I will say that, well, we're going to describe it more later, but roughly speaking, we choose the voltage across each capacitor and we choose the current through each inductor. So let's say we have 2 capacitors and 2 inductors. So it's going to be, and say they're all independent, so it's going to be a what order system? Two capacitors and 2 inductors. Fourth order system. Okay? And that's because capacitors are energy storage elements and inductors are energy storage elements. So 2 of each, 2 plus 2 is 4. Also 2 times 2 is 4, but that's not the point of this. I should have chosen 3. It would have been better because it's less ambiguous, right? So our state vector would be, so we're going to have a 4 by 1. And so we can choose, once again, any order, it doesn't matter, but as long as you're consistent. So once you choose it, you got to stick with it as your state vector. So let's say the voltage across capacitor 1 is the first one we choose, and maybe the voltage across capacitor 2 is the second one that we choose. And maybe we'll do the current through inductor 1 as the next one, and the current through inductor 2 will be the last one. So we also said n equals 4, which is the number of state variables that we have. Okay, and then outputs. Remember, the outputs are just the variables of interest, right? Maybe we're not very interested in this system and we only care about like the current through resistor 7. There's a resistor 7. But maybe we care about multiple variables. So let's choose some outputs for a circuit. So I'm making this up, of course, because we don't have a circuit. Let's say that what I care about are the following. I'm going to say I care about the current through resistor 7. Okay. That is fine. I could choose that. Let's say I also care about, maybe I care about one of the state variables. Maybe I care about the voltage across capacitor 2. Okay. That's fine. I can choose a state variable. Maybe I care about one of the inputs. Or in fact, maybe I care about some scaled version of the input. Maybe I care about what is, well, for instance, maybe I care about what the, what, I could choose anything, 6 times the current is. It would be a weird one to be curious about, but you could choose it. Maybe I care about, let's see, there's one more. Oh, maybe I care about, like, for instance, what is the sum of IL1 of t and IR7. Kind of ran out of room there, but. IR7 of t. So I can do that. Anything that I want out of the circuit, I could use as an output. We're going to have to construct an algebraic relationship between the states and the inputs. Essentially, we need to be able to construct the outputs in terms of state variables and input variables. So we'll talk about that more later. Oftentimes, our outputs are just like a couple of the state variables or something like that. That's typical outputs. Okay, so there is our sort of example, our electronic example of what the inputs might be, what the states might be, and what the outputs might be. Okay. So, since to know the state vector x is to know everything about the state, the energy stored in each element can be determined from the state. Okay? So once we know the state vector, we can determine how much energy is being stored in each energy storage element. Therefore, the time derivative, dx dt, describes the power flow, right? It describes how the power is flowing around in the circuit, or in whatever system you have. The choice of state variables represented by x is not unique. In fact, any basis transformation yields another valid state vector. This is because, despite a vector's components changing, when its basis is changed, so when you change bases, you change the components of the basis or of your vector, which is to say, you change these values of the vector. These are the components of the vector. However, when you do that, a symmetric change also occurs in its basis vector. So whatever you do to the components, you're like undoing to the basis vectors. And how many of you have already done basis changes for vectors, the change of basis? So a couple of you, not a bunch of you, but a few of you. And I'm not gonna require that we do that in this class. It's a linear algebra thing. Next semester you'll learn how to do that in linear algebra, and we'll be doing that. I'll hold off on making you do that until then. Don't worry, because it's kind of a linear algebra thing. However, this means, so this idea of changing the components but also changing the basis means that a vector is a coordinate independent quantity, and the same goes for vector valued functions. This is not to say that there aren't invalid choices for a state vector. There are. But if a valid state vector is given in one basis, any basis transformation yields a valid state vector. So that is important to be aware of, and it turns out you can construct a change of basis arbitrarily. So there are an infinite number of valid state vectors. So we chose x1, x2, x3. You could choose another x1, x2, x3, etc. That is valid. There are others that are valid. One aspect of the state vector is invariant, however. It must always have order n. So it must always have the same number of state variables. Our method of analysis will yield a special basis for our state vectors. Some methods yield rather unnatural state variables. For example, the third time derivative of the voltage across a capacitor isn't very easily intuited what that would be, right? Anytime we go over time derivatives of like 2, we kind of lose a lot of physical intuition. The way that a lot of folks will construct state space models, they end up, if the system order is like 4, they end up with third order derivatives as some of their state variables. This is part of why we use this method of construction. The method of construction that we will use will yield natural state variables. For instance, we'll get things like the voltage across a capacitor or the force through a spring. Those will be the state variables that we'll find. Technically, they're both valid. For a given system, you know, if you construct a valid set of state variables, that's fine. It's not unique. But some of them are more physical than others, are more physically intuitive for us. So we prefer to use this method to construct them. By this method, I mean the one we're going to learn. We haven't yet. Okay. Any questions on this before we do the second lecture today? All All right.